예, 행사를 2시 정각에 시작하도록 하겠습니다. This conference will be start at 2 p.m. May I have your attention, please? The Future Factory Tech Conference is about to begin, so please be seated. Thank you for your attending. I'm Injali from Korea. Today's conference is held as a related event for the ISO TC 184 SC5 meeting. The main topic of today's conference is major standards and use cases in the field of intelligent manufacturing. I think here in this conference room we have field expert as well as standard expert come together. I hope this will be a time to exchange opinion on the using standards in the manufacturing industry. We hope virtual attendee enjoy too. It's live streaming on YouTube too. So to begin this program, we are pleased to have Mr. Kyung-hee Lee, Head of Standard Division in Korean National Body, CAT, to deliver the opening remarks. Please give him an applause.
안녕하십니까. 국가기술표준원 전기전자정보표준과장 이경희입니다. 기업 업무 시스템 및 자동화 분야 국제표준화 회의에 참석한 전문가 여러분들과 함께 이번 컨퍼런스를 개최하게 되어 기쁘게 생각합니다. 오늘 컨퍼런스에서 발표해 주시는 샬로타 존슨 의장님, 베른트 웬젤 컨설턴트님, 국내 한순흥 교수님, 홍승호 교수님을 비롯한 산업계 연구소의 전문가분들께도 진심으로 감사드립니다. 아울러서 이번 행사를 주관해 주신 한국산업진흥화협회 최동학 본부장님과 관계자 여러분께도 깊이 감사드립니다. 우리 정부는 산업의 디지털 전환을 위해 올해 7월 산업 디지털 전환 촉진법을 시행하였고 관련 종합계획을 수립하고 있습니다. 종합계획에는 기업 업무 시스템 표준화 및 실증 데이터 품질, 인증 관련 내용도 포함될 예정에 있습니다. 미래 전략 산업의 경쟁력을 확보하기 위해서는 제조업이 디지털 전환을 통한 지능화가 중요합니다. 디지털 전환에서 산업 데이터의 상호 운용성 확보와 기업 업무 시스템의 통합의 핵심 요소는 표준입니다. 국가기술표준원은 민관이 함께 스마트 제조 표준화 전문가 협의체를 운영하여 표준 개발, 표준 실증 사업 등을 추진하고 있습니다. 이러한 시점에서 스마트 제조 표준의 활용, 확산을 논의하는 오늘 컨퍼런스의 개최 의미는 매우 크다고 할 수 있습니다. 국가기술표준원은 이번 컨퍼런스를 시작으로 스마트 제조 표준의 확산을 위해 국내외 협력 기반을 확대해 나갈 계획입니다. 우리 제조 현장에서 쓰이고 있는 기술들이 국제 표준으로 반영될 수 있도록 전문가분들의 표준화 활동을 적극 지원해 나갈 계획입니다. 오늘 참석해 주신 국내외 전문가분들께 다시 한번 감사드리고 여러분들의 건승을 기원합니다. 감사합니다.
Thank you for your meaningful remarks. Let's start the first presentation. The speaker is Dr. Charlotta Johnson at Lund University, Sweden. Okay. As you know, she is the chair of ISO TC 184 SC5. The topic of the presentation is smart manufacturing standardization issues. Let me start. Okay. 잠깐만요. Yeah, please give her warm welcome.
This. Hello everyone. Should I remove this when I talk here? Okay, I remove it. Okay, hello everyone, and thank you for inviting me here. My name is Charlotta Johnson, and I will make a presentation about smart manufacturing standardization, issues and trends. I am the acting chairman of ISO TC 184 SC5, a committee that is dealing with industrial interoperability. I am also professor at Lund University in automatic control. I will start with a quote. Someone said, "The pace of change has never before been this fast, yet it will never be this slow again. And I think this is true. There is a lot of technical development happening at the moment. Let me give you a few examples taken from my own lifespan and examples related to computer power. So first of all, new technical systems, they are adapted so much faster today than 50 years ago. When I was born, the television took about 13 years to reach 50 million users. Today, a game could reach 50 million users in just a few days. Speed, I mean, storing data can be done so much faster today. Today, you can store data 10,000 million times faster than you could when I was born. It's much, much faster. Also, the price has been reduced. The price for storing data has been reduced drastically by a factor 10 to the power of 8. So this has drastically changed the landscape. Today you have cheap, fast, and reliant and strong computer power. So all this has, of course, formed a platform on which new technologies can be developed. For example, AI, quick simulations, real-time simulation, 3D technologies, interoperability, etc. This is not the first time that new powerful technologies that are often preceded by research becomes available on the market. The implication is always a major shift in society. Some people even speak about a revolution. And at each occasion, there has also been economic growth and an increase in living standard. So therefore, the digital transformation that is now happening is of high importance globally and nationally. So as I said, it's not the first time it's happening. We see here the first was the mechanics that was introduced that completely revolutionized how manufacturing was done. Then it was electricity, then came the electronics, and now it's the digitalization. And this, as I said, has national implications and interest, global interest. So there are a lot of initiatives in the world, all dealing with the same thing from a technical perspective. They are called slightly different things all over the world. Many speak about smart manufacturing, a term coined in the US. In Sweden, we speak about smart industry. In Germany, it's Industry 4.0. In China, I thought it was made in China 2025, but I recently learned that they now call it intelligent manufacturing. Here in Korea, it's connected or smart factory, but they are all dealing with the same thing. This importance, I will skip this. This importance has, of course, also been recognized by the global standardization organizations like ISO and IEC. So there are several technical committees, TCs, that are dealing with topics related to smart manufacturing. But on both sides, ISO and IEC, there are also coordinating committees that are coordinating the different technical committees and the work that they are done, all under the umbrella of smart manufacturing. So on the ISO side, there is a coordinating committee called SMCC, Smart Manufacturing Coordinating Committee. And on IEC, there is a coordinating committee called SYC-SM, System Committee for Smart Manufacturing. Within ISO, a white paper has been developed, and the intention of this white paper is to facilitate for companies and other stakeholders, facilitate for them so that they can adapt and benefit from smart manufacturing and that concept. Among other things, this white paper also contains a definition of the term smart manufacturing. That is what you see here on the screen. And this is a term that both ISO and IEC has agreed upon. What does this white paper contain? Well, this white paper explains smart manufacturing by utilizing models from innovation. So with a certain regularity, there are new disruptive technologies that becomes available, just as I said before, and they pave the ground for a second wave of innovation. We could compare, we have done a lot of development on technical issues, and now industry can leverage upon those. Some of these technologies are available today. We call them enablers. Some of them are still needed and they are in their infancy. We call them enhancers. They need to be improved a little bit. And in the end, we hope to see a lot of effects of this. We call that effects. And when the effects of these new innovations, when they are large enough, they will revolutionize how things are seen and done. For example, how things are seen and done in industry. So the white papers, I said we had enablers. And in this white paper, we present these disruptive technologies that are matured enough to be leveraged on already today, the enablers, the first wave. The white paper also present the enhancers, what we need to, some design principles mainly, that we need in order to further strengthen the development. And then the white paper also speaks about the effects. I will show some of this. So we have some figures that are showing this. The enablers, these technologies that more or less are ready to leverage upon. They include, for example, AI, that today is so fast that you could have a response immediate. They include wireless technologies such as 5G and cloud computing. They include simulation. They include robotics. They include data security. Then we also have the enhancers. They are also presented in this white paper. Here we have concepts that are not yet fully developed, but are very much needed, and there are a lot of work going on. Here we see things like digital twin. We see the concept of customized products. We see concept as horizontal and vertical integration, interoperability. We also have a similar picture indicating some of the foreseen effects. Just to mention a few, we have servitization, meaning that you start to sell services rather than products. We see the data-driven business model coming up as an effect of the technical change, and also things like circular manufacturing, where sustainability issues are taken into account. So this was presented in the white paper, but also in the white paper we did, this might be difficult to see from a distance, but we also made a check. Where do we have working groups within ISO that are contributing, either contributing to the enablers or contributing to the enhancers or contributing to the effects? What we saw was that there were, for the enablers, there is a technical committee dealing with robotics. There is a committee dealing with 3D technology. But when we look at the enhancers, it is not so obvious. Sometimes there are a lot of technical committees that are working on this new concept. And that is good, but it needs to be harmonized. For example, we saw that there are 7 different working groups that are working on the concept with digital twin. That is good because it's a new concept, so we need a lot of ideas to come out, but we need to harmonize it. And when we looked at the effects, we could see that there are a lot of definitions still missing and not being addressed so clearly. I am, as the chair of SE5, I am also participating in the Smart Manufacturing Coordinating Committee. And the work that we are doing within SE5 and that we have focused on this week is the work that all the 11 working groups within SE5 are doing. So we had our plenary. Thank you very much for inviting us here to Korea. We very much appreciated it. Here we see very important working groups that are also contributing to smart manufacturing. For example, we have a working group working on key performance indicators that is important for vertical integration. We have groups that are working with the convergence of informatization and industrialization, so IT/OT interoperability. We have groups working on mass customization. We have work going on that relates to simulation and interfaces for simulation. So we have a lot of important work for smart manufacturing going on in Subcommittee 5. Let me just show you some applicabilities. So of course, these standards that we are developing, they are important for industry, and they are the base or form a platform on which the applications can be done. I am just highlighting here some cases where you see robotics, and there are many different domains. So we have advanced robots, we have collaborative robots, we have software robots, and we have human-like robots. And a lot of standards are needed in order just to control the robot. And on top of that, we also need standards for interoperability, because these robots need to interoperate with other software systems, especially if they are on the doing manufacturing, where other systems are so closely related to robotics. The same is true for augmented reality and virtual reality. Also here, we have groups within ISO dealing with AR and VR, but on top of that, we also need standards that are dealt with in Subcommittee 5, standards that are dealing with interoperability. And AR and VR is also starting to be used a lot out in industry. We see some examples here, maybe not the one with the Pokemon, that is not from industry, but the others are from industry. You could see the KPIs, the key performance indicators, live. You could scan QR codes and get instructions of how you should do, and you could have virtual pointers showing how reparation or maintenance should be done, for example. In Sweden, that I come from, we have also realized that this is important, and it is a topic where there is economical growth. So we did some examination in that area now, and we found out that there is a big value. The value for this market is almost as big as we have for chemical and pharmaceutical in Sweden. The orange one is indicating smart industry and that sector, and pharmaceutical and chemical is the pillar to the right, and to the left we have mining industry. So this industry is bigger than the mining industry. So it is very important. It's something that is growing, and I'm sure it is the same in many countries. So there is a big business value in this. As a very last slide, I would just like to give you these two examples of reading material. To the left, we see the white paper from Smart Manufacturing issued by ISO, and there is also the link where this could be downloaded. And on the right, you also see a booklet I have a copy of it here, so I will give it to you. And it's a booklet that we wrote in Sweden, and it deals with how standardization has strengthening the industrial sector and the important role it can play now in the future when industry is digitalized. It is not speaking about the detail of the standards, but rather the value of it and the role it has played and will continue to play. And there is also a possibility to download this one in English and in Swedish. And with that, I would like to say thank you, and you're more than welcome to ask me questions here. And you're also more than welcome to contact me, so I give you the contact information here. Thank you very much.
You may have a question, but due to the time limits, we are going to have a Q&A and panel discussion session in last. Okay. Now we are going to see R&D standards best practice project cases. Speaker of this presentation is Dr. Jin-Sung Lee. He is a senior researcher of Korea Electronic Technology Institute, KETI. And he is currently operation test bed for smart manufacturing in Gyeongnam province of Korea. Let us welcome him with applause. Okay,
Hello everyone. My name is Jin-Sung Lee. I'm working in KETIS, and my presentation title is Machining Test Bed based on international standard technology for application integration. This page of table contents, escape. First, I introduced to the Smart Manufacturing Innovation Center. We called SMIC. The SMIC is a test bed for smart manufacturing using the international technology. The goal of SMICs are providing a test environment for cooperation between operation technology and information technology, and creating an ecosystem in the smart manufacturing field, and last, development of a new manufacturing service model based on smart manufacturing technology. We categorize the smartization of manufacturing site into the 3 layers. The first is physical layer, and second is digital layer, and last is intelligence layer. We demonstrate equipment and system of advanced manufacturing technology by each layer, and we integrated these layers using industrial IoT technology like OPCUA, UMATI, TSN, and 5G, and so on. And SMIC operating various program. First is a company support program, consulting for smart factory technology, technical support for process innovation, and human resource development for manufacturing, and proof of concept for new smart manufacturing technology. The R&D programs are industrial IoT technology and digital twin for manufacturing, and industrial AI. The Changwon SMIC is technology development and support for smartization of the precision machinery industry. Because the Changwon city is the agglomeration of a precision machinery industry, and there are located many related companies like Siemens, Fanuc, Hyundai Yuya, DN Solutions, and so on. The figure shows location of Changwon, SMIC, and our various activity and demonstration technology. Changwon SMIC consists of two kinds of testbed building. First is demonstration building. It's for proof of concept of new smart factory technology, and the testing building is prototyping and trial production, and its total size is 3,000 meters squared. And there are operating various CNC machines and manufacturing application systems. The figure shows a list of demonstration systems related machining industry. SMIC is using OPCUA standard for data communication between facilities. We guaranteed interoperability by using OPCUA in a manufacturing environment composed of different facility and controllers. For example, we have various machines such as Hyundai Yuya, DN Solution, Hwacheon, but their controls are Siemens, Heidenheim, Fanuc. We make an integrated data communication environment using different machine and various controllers. And we adapted UMATI for communication between machine tools and systems of higher level. UMATI means Universal Machine Technology Interface. It is provide the standardized data model and structure of communication about machine. We developed the UMATI Edge and applied UMATI to the entire machining process. The left side figure shows system architecture of UMATI demonstration, and right side show UMATI Edge and UMATI information model. And we make a TSN, time-sensitive network testbed to apply ultra-low latency wire network to manufacturing sites. Since SMIC wireless network uses 5G, so the wireless network requires ultra-low latency, and we used some machine to the data collection and analysis based on TSN. The figure shows a testbed in TSN testbed. And last case of standard technology is a material standard. We're using the material standard in ISO 14955 Part 3 for research on energy efficient machine methods. Currently, we're using AI technology to measure energy consumption by machine operation patterns. In the future, standard technology such as AAS and KSX9101 will be applied to the SMIC. AAS utilized to modeling for digital twin implementation of facilities in SMIC, and KSX9101 utilized data exchange standard between manufacturing application system in SMIC. The figure shows the SMIC future system architecture of standard technology. And shows the other systems in SMIC. The first is virtual commissioning system using the digital twin. The left figure are the real manufacturing process and facility in SMIC, and right side is the virtual process and facilities. Sorry. Next is a smart workbench for higher efficiency at workplace. This system is actually used in the hydrogen vehicle parts production process. The company name is Dongyang Piston. Yeah. And last case is a remote collaboration system based on mixed reality. We're using this system for connected Ansan SMIC and Changwon SMIC. And we operating a company software program. First case is that a smart workbench and monitoring system to replace existing manual work. And second case is that edge computing for quality prediction. This video is a factory opening day in Changwon SMIC. Sorry. This page shows a representative R&D project. The first is develop standard-based digital twin framework, and it demonstrates using SMIC equipment and systems. And others is ONM platform for precious machining tools using skilled workers' knowledge. Okay. Yeah, this page is the last. Thank you for listening.
Thank you, Dr. Jin Sung-ri. Okay. Let's move on to the third presentation. 진혁, 최, and Sun Lim are the joint research team on system interoperability. They are present about machine vision function. Please give them applause. Okay.
Hello everyone. Good afternoon. My name is Jinyuk Choi. I'm from the Federation of Korean Information Industry. First of all, on behalf of FKII, I would like to thank you everyone for giving us the opportunity. I'm so delighted to be here today. The title of our presentation today is Design of Industrial Machine Vision Function Block for Application of PLC Standard for Enterprise System Interoperability. And my colleague, Sun Lim of Korea Electronic Technology Institute, will cover a part of our presentation together with me. This is the table of the contents for today's presentation. First, what I'm going to talk about today is the technology we're developing and the latest technology related to industrial automation, including industrial controllers and AI trends, as well as trends in the industrial machine vision market. The next step is a description of the need for this technology. After that, Sun Lim of KETI will continue the presentation. He actually implemented the technical part of this project. The technology we are currently developing is an integrated controller. Our ultimate goal is to integrated camera, image processing, AI inference models, field buses, and PLCs into a single hardware for real-time processing. To this end, we are developing function blocks that handle AI vision in PLC languages. Now, I would like to explain the recent development of the latest technology related to industrial automation. That is basically the background of this project. Number one, integration and modularization of writing, RANs, and software AI. Number two, AI technologies response to existing high-level inspection. Number three, improved installation, convenience, and user adjustment function. Also, if we look at the key trend in the industrial machine vision, we can find a few recent developments and facts, such as semiconductor display equipment field is currently pitch-based. Dedicated system for reliability and control, motion, vision, integration, and modularization in the facility field. Improved response and coordination of field user through AI. Simplify high-level inspection with AI. Here are some of the leading companies in the latest industrial controller and AI development trends. A to E are companies that develop hardware and produce PLC engine controller, 3D machine vision camera, AI-based vision system, and automated smart controller with built-in machine learning, respectively. F, G, and H are software development companies and provide automation solution for individual PLCs and server drive AI framework support, etc. As the market demand for AI continues to increase, the size of current global market is rapidly growing as well. We can see the demand for every kind of AI application has been quickly growing everywhere. So We believe that the potential market for software algorithms, speech recognition and interpretation, as well as image processing and recognition is huge. In addition, hardware-related service and software are all growing together. Therefore, as a spillover effect, we believe that the need for an integrated controller capable of collecting and processing industrial data for production facility automation, we also follow the suit. Let me explain the necessity of developing this technology. As you know, the automated control system of existing manufacturing facilities have been operated individually. So we are trying to upgrade it in order to integrate some system like PLC, motion control, machine vision, etc. for data collection. In this integrated controller system, the PLC is a digital actuator that controls the machine or processor. And motion control is the part of machine that behave in a given way. And machine vision equipped with AI provide automated inspection and analysis based on images. As for the purpose of the project, we intend to solve variable problems and provide improvement through this development. The high development cost, the difficulty of maintenance, compatibility issue when error occur. We are improving system efficiency, increased operational convenience based on AI tech. Now I will pass you over my colleague Son Lim.
Good afternoon. My name is Son Lim. I'm a senior researcher of the KT. I'm a second speaker of this presentation. Okay. PLC is a control device that performs a logical, arithmetic, or the sequence operation for various systems in industrial field. In general, PLC sequentially processes signal input from the outside and output the calculation result back to the externally connected device. The IEC 61131 Part 3 define the model of PLC software such as in these presentations, the configurations and POU, program, function block, functions. The PLC program defined according to the IEC 61131 standard have the advantage standardizing product over all system. First of all, let me explain the architecture of IEC 61131 Part 3 software. Software model has programmed elements such as function block and function writing in the program language defined in the standard and program implementation element. Program component include configuration, resource, task, variable, and access path. Variable defined within configuration can be shared with each other by different program or resource through the access path. Configuration is element divide system unit, and resource is an element divided by the function unit. Next, I will explain the program language, which is the core of IEC 61131 Part 3. The IEC 61131 Part 3 standard basically define 4 languages: the IL and ST languages that can be written in text form, and LD and FBD, function block diagram, language that can be written in graphical form. In addition, the SFC language is a graphical language used to express sequential pictures, such as flowchart format. You can see the basic four language form in these pictures. IR language is similar to assembler and can be composed operation instructions such as add, and operation. The IR, sorry. Sorry. Okay. The second text language is XT. XT is very similar to Pascal programming language that is commonly used when developing complex or advanced pictures. The FBD language is a language used to compose PLC logic by expressing defined function block and networks. And lastly, LD is standard ladder diagram programming and is the most commonly used PLC language in Korea. In particular, it is a language that can most intuitively define the implementation of a function for input-output device, which play the major role in PLC system. Among them, in this presentation, I would like to introduce industrial machine vision function block using FBD language. The FBD language has the advantage of intuitively describing the input and output variable of a function or a function block to make it easily to understand the function of the entire system. In addition, it is one of the most used language because even developed or operator without programming experience can easily develop PLC programs. Industrial machine vision solutions are widely used in industrial sites due to recent development in camera technology, such as 2D and 3D, and convergence of the AI technology. However, solutions are being developed differently by different manufacturers. In order to integrate the program and development environment with a standardized PLC system, I think developing standardized machine vision library are very important. We would like to take this opportunity to propose a camera function block for standardized industrial machine vision. Before explaining the camera function block, we suggest standard variable type related to camera and image. The first, camera reference, structure variable interface PLC system with the camera. Especially, it includes information on bandwidth, manufacturers, information, interface type, and camera device address. And through this, each camera can be accessed. The second, image reference, is a structure variable for define each image taken by the camera. Basically, it contains information such as image width, height, information, compression format, image size, and save address. The pixel format reference is a structure variable representing color filter setting information used when the camera creates a color image. And finally, the last table, the trigger source reference is a structure variable indicating setting information for the image acquisition start signal of the camera. Through this presentation, we would like to propose a total 5 standard function blocks related to the camera. You can see the 5 function blocks, the open and close function for creating and disconnecting the interface of the camera connected to PLC system, the 1 and 2, and the set parameter and get parameter function for setting or reading the parameter for capture the image of each camera. And finally, the graph function for capturing the image. I would like to explain each function in detail one by one from now on. The first, let me talk about the camera open function block. This function block is used to connect specific camera, has an input and output variable for each camera ID. Each function block has an execute to input parameter, and the function block starts at the signal, a rising signal when the input parameter changes from the false or to true. Also, all function block, including above function block, define done, VG, error, and error ID output parameters in the same way. Also, done is used to inform about the completion of the corresponding function block. The second, BG, expression information about whether the current block is operating or not. Finally, error and error ID output variable that tell us whether there is an error after calling the function block. If an error occurs, information about the error. The second, I will talk about the camera close function block that is used to remove or disconnect PLC system and specific camera interface. This function has the same input and output parameter as a camera open function block explained earlier this page. Next, I will explain camera set parameter. The camera is preset with the necessary parameter for taking the image by default. Especially, there are width, height of the image to be saved, and it is a color image. If it is a color image, the pixel format and determine the pixel arrangement, shape, and exposure time and gain parameter related to the image brightness, and so on. So, trigger source, there is a trigger source for setting the image saving signal, and the trigger source and camera operation method may be implemented different for each manufacturers. The set parameter function block also has the cam ID input output variable by default, and it has an input parameter from the camera I just explained up to execute. This image set parameter of function block I just explained. The left side is input parameters, output side is right side is output parameters. The camera get parameter function block is used to output the required parameter set in some specific camera. So compared to the set parameter, so get parameter has the camera essential parameter as an output parameter. This image is a get parameter function block I just explained. Lastly, finally, I will explain the camera graph function block. It is a function block used to create the image with parameter set in camera, and the image can be created within the timeout time. If the image cannot be created within timeout, the error of the corresponding function is output as true. If the image is created normally, information about the image is output as the image output parameters. To help you better understand the industrial machine vision function block I just explained, I will talk about the 3 use cases. The first is a case the parameter setting the single camera. We use the camera open function block and first create an interface to the camera connected to cam1 variable. Then After setting the required parameter for CAM1 using the set parameter function block, the interface is terminated. This picture describes the function blocks of the opening the camera. The second use case to create an image using the 3 multiple camera. The 3 camera connected to the PLC system are respectively connected to CAM1, CAM2, CAM3 with other variables. After creating an interface for each camera using camera open, the end function is used to execute the set parameter function after all 3 function blocks are completed. When the required parameter setting for each camera is completed, the camera graph function block is called create one image. So the last use case is an example of setting essential parameter for camera. This is an example where we get essential parameter of the camera connected to CAM2 and set the essential parameter of the camera connected to CAM1 and take an image and remove interface. So due to time constraint, if you any the detailed description of the work question, if you want to get to the detailed description, contact this email and last Q&A time. In order to standardize the industrial machine vision library that is not currently standardized, we have proposed 5 function blocks and variable type. Through this, I would like to suggest the standardization method for industrial machine vision development environment along with the existing standardized PLC system. So going forward, we plan to continue follow research on standard to achieve this goal as a immediate next step. We plan to propose the standard function block image processing. Thank you. Yeah, thank you for sharing us your R&D project studies. Okay, and let me check. Okay. The last presentation of session 1 is about quality issues on steel industry. 정한 Lee and Jino Kim are carrying out the presentation. Let us welcome him, please.
Hello everyone. Jino Kim is Assistant Manager of the Korea and 정한 Lee, Manager of Hyundai Steel, in charge of developing competition analysis technologies and developing intelligent flat metal technology. First here, according to the key technology trend published by Gartner, it emphasized the importance of humans. The key point is that it is changing from IoT to intelligence of things. Specifically, it refers to the digital connection of human behavior and experiencements. The field knowledge text that we are going to present is the development of technologies that digitally connect human experience. Develop of a service platform to help transform different jobs. Diagnose the information of the customer who want change job first. Current duty, certificate, experience. It also identify the basic competence level associated with the customer desired job. Job level diagnosis is conducted online through multiple choice and subjective methods. NCS and Hyundai Steel CS, which are job analyst standards, are used and work manuals are used in the company. Receive the customer job change and job change desire errors. It is important to understand the availability, suitability of the desired field of work. Identify the basic job competence level and problem-solving job competence at this stage. The measurement method presents a case and diagnose the problem, analyze ability. It also identifies the availability to deal with the situation. Job competence identification will be conducted through an interview. Use fault report within company for objective diagnosis and use expert analyst opinions. We did the job analyst first for the customer turnover. First, we deliver basic job relation elements. Second, I did in-depth job analyst. The job analyst STAR PS technique was introduced during the in-depth job analyst phase. S is situation. Situation presents a situation. Description of the work environment elements for the problem solving. T is task. Task describes specific issue. A is action. Action describes how you resolve the problem situation. R is result. If you have solved the problem, result describes the solution. P is prevention. Prevention describes how to prevent the same problem. Safety explain if it should be done to prevent safety accident. STAR PS will be objective data reflecting the needs of the site. We will make effort to upgrade through job analyst, manual work, regulation, and accident report of the objective data. We are developing turnover service platform through job analyst. The technology development consortium is as follows. First, KTL, service platform architecture design, user-friendly UI UX development. The second, Korea and Dual Consulting, analyst and investigation of the core competition based on industrial field knowledge, and analyst of the standard status of the core competition indication in industrial sites. The third one is CATI. CATI utilizes text mining technology. Interdependence analysis is performed by analyst, manual, and customer interview. Leverage text mining result to visual job association. Hyundai Steel as demonstration agents share know-how such as measurement, control, and hydrogen process within the manufacturing site. It was an introduction to the development of the core competition analyst technology between industry for the assessization and spread of on-site knowledge in the manufacturing industry. We are in the era of digital transformation. Hyundai Steel 정한리 will present the development of the intelligence flatness method technology to help digitalize the manufacturing site.
Hello, hi. My name is Jeong-Hwan. I'm the senior manager of the Hyundai Steel. We'll explain the technology that can apply field knowledge to the equipment. First, it is on smartware intelligent flattening management system. In the steel manufacture industries, steel products are important quality factors such as shape, length, and dimension. Among these, the shape is among these, the shape is measured through the laser sensor and camera. I will explain the background of the developing the intelligent flatness management system. Industry, flatness management systems are mainly used in the USA, Germany, and Japan. And there is no problem is producing steel product. However, it is not equipped with a special function to improve future manufacturing. Competitiveness, for example, laser lifetime prediction, auto zeroing. In addition, the system is not configured to the incorporated IoT, big data, and AI. So we promoted joint development with Palmatech, the company name, the professional development company, for the measuring device incorporating new technologies such as AI, IoT, and big data system. We'll explain the intelligent service in the intelligent instrumentation system. The item that require maintenance in the operating, the flatness measurement system so far as follow. We anticipated that predictive maintenance will be possible through intelligent service. And with these intelligent service, productive and maintenance efficiently are expected to increase. This part is the problem. We will improve the here. Next, we will explain how to integrate the knowledge association technology described above with the measurement system. Describe virtual sensor technology. A virtual sensor is a software sensors created to redundant of or replace a real physical sensor. A virtual sensor is different from the software sensor made of the mathematical model for simulation. Virtual sensors are created through machine learning algorithms based on data such as pressure, flow, and temperature generated in the manufacturing process. A virtual sensor is different from a software sensor made of the mathematical model for simulation. Virtual sensors are created through machine learning algorithm based on data such as pressure, flow, and temperature generated in the manufacturing process. So the virtual sensor can be reflected the characteristic of the production line well. In the aforementioned intelligent flattened system, intelligent services are developed through virtual sensor. As of an example, let's talk about the case of laser swimming prediction. Run by linking the output signal of the laser sensor with the flatness measurement factor of the product. This allows you to distinguish between normal output and abnormal output. As a result, the life cycle of the laser sensor can be predicted. Another intelligent service example is auto zeroing. Since the zero-point adjust service is the standard for the measurement instrument, it is frequently checked. It is mainly realized on human experience or perform zero adjustment when an abnormality is discovered. However, auto zeroing does zeroing based on the fast learned information that may have predicted unusual reading. This screen is a virtual sensor screen for the intelligent service in the intelligent flattened system. The virtual sensor measures the lifetime and 0-point abnormality of the laser sensor. Of course, there are no physical sensors that measure beyond the lifetime or zero. So virtual and physical sensors are complementary. Implication for the development of intelligent flattened system using virtual sensor will be discussed. For future smart factory, sensors must also become intelligent. In addition, many virtual sensors that reflected human know-how and knowledge are needed in production system, plant. These virtual sensors supplement the primary physical sensor, and it can reduce people's mistake. Their development are expected to improve manufacturing competitiveness in the future. This, it was carried out of the industry technology innovation project implemented by the Minister of the Trade, Industry and Energy. Yeah, thank you.
Now we are going to have a break for about 20 minutes. So we are ready. The cookie and coffee in the lobby. Please enjoy it. And we will continue the conference at 3:40. Yeah. See you then. Okay. 커피 브레이크. What?
요거 맞으시죠? 네. 몇 번 이쪽이신가요? 네. 예, 요걸로 변경해드렸습니다. 네. 예. 네, 알겠습니다.
We are going to start the session soon. Yeah, please be seated. 왜 안 넘어오죠?
어떤요? 아 이거 화면이요? 화면이 이미
너무 많이
있어서
띄워놨구나.
좀 삭제 좀 크겠습니다 몇 개.
네.
이거 네 이번에 잠시만요. 케이스 탭. 예. 예. 한번 풀어주시겠어요? 맞으실까요? 네. 준비됐습니다.
Shall we continue session? Okay. We are going to listen to the presentation from Dr. Sunung Han, who is the president of Korea STEP Center and honorary professor of KAIST. He is also ISO standard member of TC 184 SC4 industrial data area. Please give him an applause.
Hello again. I'm trying to explain about the project running inside TC184 to develop a standard for PLM MES interface. So I'm trying to introduce the SC4 activity first, and then why I'm doing developing a PLM MES interface, especially based on shipbuilding industry. And then for this interface, the project team is trying to combine PLM standard, existing standard, and also MES existing standard. And current status of project is developing a two part 1 and part 2. And then we'll show you. So this is a structure of TC184. You already know this. But under SCC4, there are several more than the figure. There are working groups. Among them, working group 16 is I'm doing the convener job. So based on this convenership, and also I trying to make a visualization-oriented interface. You also see that there is a working group for digital manufacturing. You may have interest on this. And also manufacturing management data. I guess this one is joint working group with SH5. And also SH1 is, you already know this, step NC, numerical control. And SH4 is developing 30 ongoing project. We already did more than 700 standards. So it is a rather big subcommittee inside the ISO. Let me show you a video which shows the activity of SH4.
We live in a connected world. As we move about our busy lives, almost every action that we take generates data. And that's also true for the machines that help us, whether it's the ones we see every day or those that work out of sight. They may not be visible, but they're trying to tell us something, capturing data about time and place, how they work best, and how they can be improved. This is the world of industrial data, and it's at the heart of the ISO committee dedicated to helping industry make better decisions using better quality data. You can't see industrial data, but we can use it to create a virtual representation of the real world and the things it contains. This parallel universe offers untold possibilities, providing a safe space to ask the question that has inspired innovators since the dawn of time. What if? We can model scenarios, ideas, and solutions in a way that is creative, cost-efficient, and above all, safe. That's essential in industries where we can't afford to get it wrong, where lives are at stake. But it also helps with the day-to-day stuff, putting into our hands a greater choice of products and services than we've ever had before. Huge quantities of data are generated, and in order to make practical decisions, we need to improve and sustain the quality of that data. We know that the biggest and most complex questions can only be answered by working together, exchanging data between specialists who can work as a global team, unconstrained by walls or borders.
So I hope you can get what SH4 is doing. And this one is activity inside Korea. You see that under STC 184, we have 3 active subcommittees. And Korea Step Center is working on SH1 and SH4. And Korea, who is running this conference, is in charge of SH5. And for the project I'm running, I'm trying to explain is about PLM MES interface. Currently, we found that the PLM and MES, there is no direct interface. And there was no need such interface because at the era of mass production, usually the design is done in early stage and fixed, and then production is doing massive production without never change the design or very few changes. But nowadays, as smart manufacturing is going on, we see that the personal production is more popular, so that we need a more direct interface between design and production department. I'll explain a little bit more. So the personalized production of Industry 4.0, that is changing from mass production to mass customization. One problem of this is the design level of maturity is lower than before. For the mass production, you should be quite good design, starting from before starting mass production, so that there will be more chance of design changes, so that you need to have a more good communication between departments. This is a well-known slide which shows what is personalized production. And currently, I found that Siemens has a product to have a PLM and MES or MOM. See that this is MES and PLM. It is a company product name, and there is a interface software product. So we may need to develop a standard. Turn to the Korean side. About 20 years ago, there has been a massive introduction of ERP and 3D CAD system into the companies and industry, especially for small and medium industries. And about 10 years ago, there was another era of introduction of PLM systems. Nowadays, in the smart factories project, there are many MES systems introduced to small companies. So that we need to have interoperability between those systems, ERP, PLM, MES. But ERP and MES interface is covered by IEC standard. But PLM, MES, as I showed you, that there was no few interface. This is one use case or problem case coming from a shipyard. I found that there should be, because shipbuilding or building construction, this is a personalized production. One design, one production, not mass production. So that from the beginning or from early years ago, they are doing many design changes during production. But now I found that they found problem cases in when the production stage, but reporting system is not good, still not good, because of many problems. Still they are using papers, they are using, they cannot use a personal smartphone to capture the images. Same one. And so that they are changing between design department and production department emails. But anyway, so that there is delays. And so that we need to have a three-dimensional interface. Especially design department are working on three-dimensional world. And also production department is also working on three-dimensional space. But ERP does not do such a work. So that is a problem. And additional problem is outsourcing. More and more byproduct is outsourced to the small companies. So that, and there is a coming of finding of errors. How can you communicate with the original design from the main company office of design office? One company trying to develop using a tablet that can be brought in the yard at the construction site to show, to see, to find, to capture the information there. So that the project I'm doing is that there is a two-part. One is part one. I put visualization focused on PLM MES interface. One is an overview part, and that is second one is more focused on plant or shipbuilding industry, the error feedback using three-dimensional feedback. So this one shows small contents or chapters of part one and chapters of part two. And existing standard for PLM is coming from SH4. This is AP PLCS, and they have a schema like this one. And the MES standard is coming from SH5, and this one is also a schema of this kind of structure. And among them, I'm trying to find the common items, right, to make an interface between them. And trying to make a scenario for exchanging data between PLM and MES standard. We made a small pilot implementation using open source PLM system and MES system. And the use case is coming from a shipbuilding company with piping and valves and other items. And the current version has a small schema development between common items between two existing standards, that is about product and process and resource and feedback. So that more detailed schemas looks like this one on product structure, process, and resource. and to exchange information between us and participation. Slack is used in addition to the ISO website to exchange and share information. And then part 2 is recently has a C developed inside the SH4. So that is the current stage of standard. Okay. Oh, I'm too fast to finish up. This is the final slide already. About part 1, that is an overview, and that is under doing. We did this year. We had a comment resolution meeting in June with working draft. Second comment resolution meeting in July. And then publishing means not ISO publication. It is public release of draft. And then now we are doing, so the ballot was passed in about May this year. So that we are doing a publication process together with, there is a quality committee inside the SH4, so that we are checking the formats and other items, editorial items, not technical ones, so that part 1 will hopefully can be published by ISO by end of this year. And part 2, and because there are more commentaries coming, so we may start again of edition 2 of part 1. And finally, I hope, because MES is developed by, standard of MES is developed by SH5, I hope this standard need participation and review by expert of SH5 and also TC65 or IS. All right, thank you very much for your attention.
Thank you for sharing your study on the standardization in SC4. We are going to listen to the 6th presentation. 석근 Cha, who is Vice President of ACS Corporation developing MES solutions. Okay, please give him applause. Okay.
Good afternoon. I think this time is looks tired because of so many sessions coming through. So I'd like to give you a very simple keyword we are currently developing and using a use case. First of all, I'm very glad to meet Charlotte Johnson. Here we first time I met in 12 years ago, and in Spain, Nunde city. So I'm very glad to meet her again in a very nice place in Jeju Island. Okay, today I'm gonna sharing with you about four agenda. One is who is ACS, and second is why KPI MOM ISO 22400 is important, and we implement a use case. First of all, ACS we established in 1988. First time we installed and the deployment MES. At the time, we called the assembly line control system in Hyundai Motor and Kia Motor. Also, we have a production control system, real-time production control system in Polsko Gwangyang. That's we first start. And so far, currently we have 1,800 local and overseas project has been performed. ACS Dabom is the name of trademark in ACS, which is we call the Korean word of see all in factory activities. As you see, we have many first use case, first development case in international R&D. Also, we have certified from Korean government, including Korea Advanced Standard Technology, also ISO. This is a very interesting chart today I'm going to share with you. As you know, important standard is very important in implementation of Industry 4.0. Right side, you see the Japanese people mention about their Kaizen. Kaizen is we call the continuous improvement process. That is very important. Real-time closed loop in productivity in factory floor. They try to announce the 5 level of how to implement to the from work manual to the supply chain. Interesting is they using based on 22400 KPI for MOM and MES standard. That's Professor Han already mentioned that. As a matter of fact, according to Gartner report in 2020, it is expected that more than 75% of manufacturing data will move to the edge by year 2025 due to the technology change using, you see the 5G. Today, last news mentioned about most Korean government little concern about expanding using of 5G, but 5G is the most potential application in covered latency, high-speed latency application, interfacing device to the IT system. And IIoT and the hard real-time and the industrial edge is a very new technology applied to the smart manufacturing area. But right side, you see the interfacing with some of CNC machine, but old machine does not have any interfacing card or device of a system. That's we have think about how to apply to the integration. Also, interesting is Harvard Mass 2019. More than 70% of legacy machines not connected. Some of Professor Han already mentioned about the MES is we have like this 5 layer of ISA 95 or IEC 62264. Most of people focus on that kind of architecture, but I believe I already mentioned about the IIoT or real-time, hard real-time, or 5G application gonna change to this kind of application. You can see the one of big data, like they mentioned about long-term data, and short-term data is small data we call. It is very interesting idea of closed loop. Most of people mention about smart manufacturing needs long-term data, like big data. But industrial age, nowadays most of people talking about the industrial data is we using a hard real-time closed loop. So before, many of the people apply to the MES or plant operation system is using a silo application. That's a big problem of data integration of a whole enterprise. So horizontal data management is very new paradigm shift of integration of whole of manufacturing data. So we call the post-step like identify, capture, and sharing and use. This is we have been developed with some of small manufacturing area for standard-based reference architecture for factory operation in advanced manufacturing applied to the standard. One is JTC. One is sensor network. Nowadays, is changed the name. Sang Liu from Atri. This guy has been governor of this area. That's we focus on how to integration with IIoT with production process. Also, we using KPI for MOM, and Charlotte Johnson mentioned about 2140. That's another interesting standard for manufacturing data handling. That's the energy management system. So this is one of two of them is a standard for reference architecture. I already mentioned about ISA 95 is for cloud service system. Here is interesting is big data for predictable quality and predictive maintenance. This is KPI for quality, cost, delivery, and productivity. Using a this we call the KPI loop for continuous improvement in manufacturing area. There's real productivity in our manufacturing area for manufacturing innovation service. This is a simple configuration how to integration with KPI for MOM. Here is KPI for production, and KPI for maintenance, KPI for quality, KPI for inventory. That's four major function. Nowadays, we adding energy area for KPI. That's we very interesting in application to ESG nowadays, energy, environment, social and governance area. I believe manufacturing area needs that standardization. This is one of we actually and my company we developing a very high level of how to managing of manufacturing data integration integration for smart factory. We divide here is automation and hybrid and manual. I believe, as I mentioned earlier, our current manufacturing machine does not support integration. So we need manual data handling is very, very important. Also, hybrid area, how to we adding IIoT application or device to the area is very important. This is digital twin. Today, I believe we first time we're gonna explain about this system, but we didn't. ISO digital twin for manufacturing framework, ISO 247 is very, very impressed me about the application, how to find the manufacturing data. They divide by dynamic and the static and the mandatory and optional. I believe we can adding our current TTA standard move to this area is very next step to maybe we think about the application expansion. This is very one of a simple chart how to plant operation area apply to the standardization to the advanced smart manufacturing reference model and LAMI 4.0 model. I'm going to simple introduction about the ISO 22400 KPI for MOM standard. We have a four part. One is overview and concept and terminology. And part two is definitions and the description of key performance. Part three is template and category for KPI. Exchange and part four is exchange and use of KPIs. This is a red box is we are focused on apply to the KPI for MOM area. As I already mentioned about a simple introduction, this is more detail about KPI. What is KPI? Consist of detail schedule and the job order data, production data, material data, and quality, work time data, process data, and equipment data. And that's a level 2 interfacing. This is a little old one, but at the time, 35 KPI. 9 of efficiency indicators, 9 of quality indicator, and 4 capacity index, 4 environmental indicators, 6 inventory management indicators, 3 maintenance indicators. This is one of time model of KPI for MOM. Here is a timeline for a work unit. This is a timeline for production order processing, timeline for worker. This is a logical relation. So we have a format how to calculate of KPI. So most of people using a common formula calculate of same performance in a different manufacturing or a different factory or different plant manager. This is another standard for effect model diagram. So this is one of the example of overall equipment effectiveness of how to effective diagram move to data and something. This is standard calculation method, as I mentioned, and I like to introduction about the use case. Japanese people already mentioned about how to advanced smart manufacturing level divide. So I think this is one of the idea how to implementing of autonomous intelligent manufacturing for level 5. One of the case we using textile industry, we developing some of KPI KPI, how to integration of KPI using IIoT and edge computing, and integration with dyeing process and drying area. Also, another application area we using big data and 3D visualization for digital twin and quality production intelligent. This is a calculation method of how to we can calculate of KPI for MOM. This is a simple application of data. Interesting is you can see the what's going on production area. Red means some problem in an area. Green is goes smoothly. So this is one of the example of production operation. This is one of area of a bar chart of learning or downtime or something like that. This is a very long-term view of operation. This is learn and downtime of area. So this is one of the examples. So most of people want to see the graphical or monitoring by graphically. So this is we already implemented the KPI for MOM in textile area. This is my presentation. Okay. Thank you.
Thank you for your presentation. Now let's move on to the seventh session, and I would like to introduce the speaker, Bond Wenzel, working for ASAM, which is a non-profit standardization organization in Germany within the automotive industry, and he is participating in ISO TC 184 SH5 as an expert. Yeah, please welcome him.
Hello, everyone. Thank you to CATS to give me the possibility to tell you something about ASAM. ASAM stands for Association for Standardization of Automation and Measuring Systems. It's not a German organization, we will see in my presentation. And special thank you to Director Kyung-gi for the warm welcome. So let me look. Oh yeah, okay. So I will give you first of all a short overview about ASAM. I will then tell you something about the classic domain activities and about the, I will stand here, about the OpenX activities. Of course, in 20 minutes, I cannot tell you about anything about the details. I hope the sheets will be distributed and I will not run away after the presentation. You can ask me then also about different things. Does it operate or not? Okay. So, ASAM, also, das geht so nicht. ASAM was founded in 1998, and in the meantime we have more than 400 members from all over the world which works together in a non-competitive way. We have OEMs, we have tier ones, and this means the users and the implementing companies of the standards work together. Here you have a short overview about the members of 2022 which arrived. We have also members from the Korean side. I think the company Star Meta is one of the industry companies which is present inside the ASAM EV. And we have, of course, a lot of strategic partnerships for the things which are standardized. For example, in ISO, for this TC 184 SC5, we have an R liaison, but we have also other C liaisons with other ISO gremiums which are necessary for the different standard developments. I will not speak about the development process, how it is organized. Here you have a lot of information how a standard will be developed. You can compare that at the end with the ISO stages, but we look that we are a little bit faster, and that's why we have different kinds of reviews. So we have a kind of review for the requirements at the beginning, because we distinguish between active participants and passive participants. And so the passive participants can at the beginning formulate what should all considered, how it should look like, and at the end they can look if it is fulfilled and in which way it is fulfilled. Here you have now the detailed overview about the standard portfolio, and you must make a simple division in two parts. This is one, the simulation area, which is the new area, and on the other side, all the other areas are shown as the so-called classic domains. What's the main difference between the simulation area and the classic domains? In the classic domains, we have a classical model, which means at the end, the standard is available as a PDF document, and you have, like in the ISO 2, to pay money for the standard when you want to receive it. And in the simulation area is everything for free available. But, and that's an important topic, the people which wants to develop a standard must be an ASAM member. Without an ASAM membership, it's impossible that such a standard is shown. So let me tell you something about the different areas. Measurement and calibration is one of the oldest domains, and you see this is the listing of all the standards you will find on the homepage. I will tell you today something about the latest developments which was done and the latest releases. This is the so-called CMP standard for measurement calibration. In the diagnostics area, which is responsible for the diagnostic of the car, I will tell you about something, the SOVD standard. I will look to the test automation area and tell you something about the OTX extensions, and then I give you a short overview about the simulation area. Yes, so let me start with SOVD. Why SOVD is introduced? SOVD stands for Service-Oriented Vehicle Diagnostics. If you look for such a upper class car like you have it here in the foyer, I think it's a Genesis 90 if I remember me correct, in such a car you have, I think it's better to see on the next page, you have a lot of so-called ECUs, and these ECUs are connected in different networks. But in the meantime, it has changed a little bit. You have not only the ECUs, you have now also the HPCs in the car, and the HPC stands for high performance computing, and you can compare it at the end with your computer at home. So this means you have operating systems, you have multi-core, you have virtual machines, and so on, and in the running of this car it must be analyzed. And in the past this was done, who knows it better, it was done first of all via diagnostic services. So a diagnostic service is communicating communicating with a request and response to the ECU. For the diagnostic services, you have a so-called description. It's named ODX, which is also standardized in ISO as the 13, yeah, the number but it is standardized in the ISO. And then you have, I think it's also better to see on the next slide here, you have, for example, a so-called D server in the ISO named MVCI server, and via this MVCI server, which read in the data description, you have then the possibility to execute the services. And on the other side, you have then an API, and with this API, you have the access. But you must know, to have a simple information, what you have to do, you have to first to select your vehicle description, then you have to create a so-called logical link, because the logical link is the physical connection to the ECU. You can have more than one of these communication links at one time. Then you have to create a diag service, you have to execute the diag service, and when the diag service is executed at the end, you want to have the results. This is, of course, everything to complicate. The goal of the SOVD is to use a modern technology to have an easy and flexible data access by the client. And this was the simple goal. And we show here we are not restricted to the classical proximity access. Proximity means you come in with the inspection, and with the inspection is then looked which errors are available. It's the typical task to read out the faults, which happens in the meantime. Sometimes the faults are going away, sometimes they are coming back. No, this standard shall be used also in the remote use cases, and remote means you can look from here to Africa what happens in the car. Of course, you should always remember that there are some security requirements which must be fulfilled, so have no fear, not everyone can this. We speak here only about the interface directly to the car, not what happens with the data which you catched afterwards. This is regulated in other standards, and also it's used in in-vehicle use cases. And the in-vehicle use case is also something which is new in the car, because this means that your so-called tester is directly in the car integrated, and so you are independent from the garage where you go, because you know the problem that we have a free market required, especially on the US side. And in Germany, it looks that the people goes, if they have a Mercedes, in the Mercedes garage and so on, with a special equipment. This is the goal behind. And the standard, of course, is not restricted anymore to the after sales based on this. No, it's also used in the engineering, manufacturing, vehicle operation, till the recycle, also the end of life, and of course also regulator use cases. Some short overview about this. We have used, and I think this is only short named here, a REST-based approach based on HTTPI, and this is similar to an open API format. We working on a so-called template level. What does it mean? In the standard itself are the different methods described, and based that we follow this this REST-based approach, we have only the CRUD methods, which stands for create, read, update, and delete. And of course, with this methods is described to which data you have access. But, and I think this is the first, we have here a so-called capability description. And the capability description defines exactly which so-called entities and resources are in the car available. And only these resources can be accessed. It's not any more visible to see with which diagnostic service it's accessed. You have then a simple resource, for example, the motor temperature, and you can access this motor temperature. And of course, this was now an easy example. It can be much more complex, that it is a structure with a lot of different elements inside. And this, of course, fulfills then the classical fault handling, where you have this environment data. Typically, we can read and write values, but of course only the values which are described in this capability description. A configuration is possible. This can be, for example, manifest files. We can have the access there as bulk data or as parameters. We have the possibility to control of operations. This you must see like software programs. And that's very interesting, because the software update is completely done in a new way. This means the responsibility of the software update goes to the car. You can compare it simply, I have it not with me here now, with your mobile, because your mobile says simple to you, an update is available. Then you have only the possibility to decide now or later, and then everything shall be done, controlled by your mobile itself. And this is the way how it should be handled by the cars also in the future. Yes, and last but not least, we have here the access to the logging machines. The standard itself is now published in the first version. This was in summer this year. We was also in the ISO TC22 SC31, where we have a so-called C liaison, and there the standard shall be also standardized as the ISO 17978. It's a little bit tricky at the moment, because independent that it was worldwide developed, as there was, for example, GM, Ford, Tata have taken part, and of course all the Germans, Volvo have taken part, but there are other countries in Europe which have a little bit problems with the standard, but it's only the access things of the data. There is just now in parallel a meeting where a little bit new work item proposal is reworked to have a success as next. So this was, I think, the first standard. I hope I have nothing forgot what is interesting. Now we come to a second standard. This is OTX. And OTX is simple. You can see OTX as a possibility to write a test specification and to describe the test logic. And the test logic shall be exchangeable. I think this is, we will see it many times today in the standardization. Exchangeability is one of the driving factors for standardization. That's the goal. And here you have the advantage that in OTX you can exchange this test description, and it's independent from the implementation. So the implementation can be done in Java, the implementation can run on an embedded system with a mono platform, and so on. This is something which is completely decoupled from this, and so this test sequence can at the end used on different target systems. Here you have an overview. It's of course also an ISO standard, and you see, let me look, yes, the white things are the so-called extensions which are standardized in the part 3. These are the standard extension, or let me start here with the part 2. The core data model is defined. It's something like a DSL language. And this language have an extension mechanism. And this extension mechanism allows that every time a new extension can be added. So it's something like a migration platform which you can use for different tasks. And with part 4, and these are now the black boxes, are new extensions standardized, which will go into the revision 2 of part 4. This is expected, I have it here on my paper, expected for end of 2023. So what is important here is more or less that we plan at the moment also new extension. And one of the new extensions is of course the SOVD extension, because then I have the possibility to use this functionality which is described via SOVD also in complex test sequences. I must hurry up, I see it. So we go directly here to the next standard. This is the capture module protocol, and here we have a good bridge because we have seen today one standard which was presented here, which have shown us how the camera data are used, and this standard here is used for different interfaces for sensor data. It is, and one of this is of course in the camera area GigA Vision or MIPI CSI 2 DeFi. So what is the task of the standard? Here we have now the picture again with the classical ECUs. At the end you have a lot of in-vehicle communication, and this in-vehicle communication shall be monitored. I say simple, monitored. At the end it should be logged, but it should be not influenced. So this means you cannot send here any XCP command, because this XCP command will directly influence the data inside this car. So that's my wording, it's simple like a monitor. This is called a probe. Or here in the standard it's named capture module, and with this capture module the data are taken out of the buses, and then these data are transmitted via a high-speed interface to the so-called data sinks, and in the data sinks you have then the possibility of evaluation of this data. This is not shown here. You have simple defined the protocol between these capture modules and this data sinks. I think here you see it a little bit better, because you see here we have CAN, FlexRay, we have here SPI interface, we have a LIN interface, and of course also this camera interfaces, and it's only defined there the protocol, but of course a little bit more at the end, because what I told you was only the data messages. We have also for this protocol defined additionally messages where you can influence this data stream itself. And important is, at the end, based on the exchangeability, you have for a big car the possibility to buy different of these capture modules which are specialized for some in-vehicle bus, but if they follow all the same protocol for the transmission to the data sinks, in the data sink you need only one evaluation process for this. I will not show you, go here to the details of this. I think we can skip this. We come then to the MDF. This I will make also very short, because MDF is the logical next step. This is a data format for the storage of the hex data, and this is used then for the data storage in the data sinks. Till MDF is worldwide also used, and it's now extended exactly for this new data from GPS, radar, LiDAR, and cameras, that this will be also storage. So we go now to the simulation area, and I give you here a short overview. I think this will be interesting because this is a complete new area of the ASAM EV. So we start here with the roads. This is the simple description of the road interface, and we have then OpenDrive. And here I can give you only some counting because that's the most what's not seen. OpenDrive is used for the development in this ADAS and automating driving area. And 90% of all streets which are modeled with or described with OpenDrive are artificial streets, are not the real streets. The real streets is simple to describe. This is something like a diligence work, but the most streets which are described with OpenDrive are artificial streets. So you have then at the end a road network containing on lanes, and especially the junctions are then very important, and this is the basis. We come then to Open Scenario, which describes the dynamical behavior on the street. So for example, you have a scenario, very easy. You have two lines. in one direction, and you have one car, for example, with 80 kilometers per hour, and you have a second car behind with 100 kilometers per hour, and this car wants to pass the other car. So, but this is not, this listen very easy, but at the end, the car changes once the lines, and he passes the car, and then he changes the lane again. And this is all described, and on this very simple example, you see you will have a lot of parameters, and these parameters then all described in scenarios. And here I jump up because I see it's running. You have here the distinguish between the concrete scenario. The concrete scenario was something like I described you now, with this different speeds, and of course you have more parameters because you need the distance from your car to the other car and so on. And a lot of such scenarios are described, and this is very important in this development process for the homologation, because at the end with the homologation it should be guaranteed that your car in all safety critical situations operates correct, and therefore you must find out the correct scenarios which shall be tested and also the parameters, and that's why we have here such an abstraction from concrete, logical to abstract. But this is an extra presentation. If I should present this completely, it's impossible here in the time. So based on open scenario, and this is now also something which you must always have in mind, the scenario is only a description. At the end, the task is that all these scenarios shall be run automated step by step, and that you have at the end an evaluation of this scenario. Therefore, we have here open label, first of all, and open label is nothing else as the labeling of the objects and scenarios, so you have the possibility to make it in a shorter area. But you have, for example, the same situation with this bypassing a car. You can have in sunshine, you can have it at rain, you can have it at snow, you can have it on a straight line, you can have it in a corner, and so on. There are so much possibilities, and therefore is a classification necessary. What ASAM is now starting is here ODD, the operational design domain, which is the next activity which comes. You found everything also on the homepage without a membership and can look to the details of this. I can only give you a hint, and sorry, therefore, here's the heating line a little bit wrong. No, not here, in the next, because I think this is a paste and copy and paste error. ASAM have started an activity which is called test specification and have the task of evolving landscapes of collaborative testing for ADAS and AD, and this is something like a blueprint. Here's everything collected also from ISO and other standardization activities to have first of all an overview what all is existing. And based on this, the new activities are now started, I think next year. In the next time will be there some workshops, and the workshops are always open. Everyone worldwide can participate because there's also a remote possibility normally on these workshops to bring in then such testings. That's especially the automation in the background. Last but not least is, we have 2 slides more, I forgot it. You can download a sim guide which shows you a better overview as this was possible in this short minutes about the simulation. And the last is a hint. Next week will be the International Conference of ASAM in Dresden. I think, I forgot now my papers there. There will be also minimum 4 participants from Korea, and I think the Yonsei, sorry if it's not correct, the Yonsei University of Korea will also present there something. And the main focus of this conference is also ADAS and AD certification. So I hope I have not too much time overtaken. So thank you very much.
Thank you very much. We have learned about German automotive industry standardization from your presentation. Now it's the last presentation. Director Jong-hyun at Ujin Prime, which make injection molding machine, will be present for us. Please give him warm welcome. Okay. this.
이거 화면 잠깐.
Wait a second. Okay. This.
Nice to meet you. Allow me to introduce myself. I'm Jong-hyun, Director of Ujin Prime Research Institute. What I will present is data model construction and application examples for data model construction and application examples for intelligent injection molding system. Ujin Prime is a Korean company that specializes in developing and manufacturing plastic injection molding machine. We sell more than 2,000 injection molding machines worldwide per year. We have been carrying out the edge-based intelligent injection molding operation system development to be jointly used for core manufacturing equipment project by forming a consortium with the following companies and research institute and school. With the support of the government since 2021. One of the goals of the above project is to develop an edge controller that data on injection molding machines and auxiliary equipment are collected for each product. Then, learning through artificial intelligence algorithms and modify the process of the injection molding machine by itself. To this end, edge controllers collect and manage data through various communication methods such as OPC-UA, Modbus RTU, and Modbus TCP, and I would like to introduce this part today. The injection molding process consists of closing the mold and injecting and pressurizing molten resin into the mold, and cooling and charging for next process, and opening the mold and taking out the product. Of course, this is the most basic process, and in reality, depending on the structure of or shape of the mold, it is much more diverse and complex, such as injection twice or inserting films or parts. Factors that affect the quality of the injection molded product is mold clamping force and melting temperature, speed and pressure during injection, and uniform pressure during charging, and so on. In addition, the mold side should maintain an appropriate mold temperature to ensure the surface quality of the product. And it is good that the raw material resin before melting has as much moisture removed as possible. For this, when producing injection molded products, various auxiliary equipment such as a mold temperature controller, a low material dryer, a takeout robot, and a hot runner controller work together around injection molding machine. Data of this equipment must be integrated and managed by each product to ensure the quality of injection molded product. Based on the operator's experience and the know-how, the current work site determines the quality of the molded product and adjusts the molding parameters and the auxiliary equipment. This form contains the problem of changing product quality according to the change of operator and the problem of inconsistent judgment and action on defects. In this development project, we install vision inspection equipment and develop edge controller that collect and store data from injection molding machine and auxiliary equipment to assist or replace worker in their work. The edge controller use the collected information to perform artificial intelligence techniques and then send the command adjusted for good product to injection molding machines and auxiliary equipment. When performing artificial intelligence techniques, they transmit data to the cloud and receive feedback. Next, we will show you how we've implemented it to collect data from injection molding machines and auxiliary equipment with the edge controller. This is edge controller. Edge controller hardware was implemented by installing Linux operation system on embedded PC. Communication and the database software was either developed by us or implemented using open source. In general, auxiliary equipment such as a mold temperature controller, low material dryer, and water chiller with communication function support RS-485 communication. Therefore, we developed and applied RS-485 to Ethernet converter that supports 4 channels. It is possible to use commercially available converters, but we developed them separately to facilitate protocol modification for each equipment. Modbus TCP protocol was applied between converter and edge controller. The product takeout status of the takeout robot is monitored through Modbus TCP communication. If the takeout robot has a function to measure the weight, it can also collect the weight information of the injection molding product. The vision inspection equipment determines the type of defect and the degree of defects of the produced product and transmit data to the edge controller via Modbus TCP. The edge controller runs and analyzes this feedback and other data together and command the injection molding machine for calibrated injection molding conditions. Currently, we have developed a judgment function for 2 types of defects, short shot and burr, and we will add the other type of defects through continuous development. Finally, The injection molding machines exchanges the largest amount of data with the edge controller. The edge controller and the injection molding machines can selectively communicate OPC UA and Modbus TCP. And the OPC UA node ID and the Modbus TCP address have been configured to be one-to-one correspondence with each other. Next, I will explain the data model between the injection molding machine and the edge controller that we built. This cannot be absolute, and there will be a lot of modification and supplement in the future. But at this point, we have constructed an essential and simple data model. We believe that the same concept can be applied similarly to other production equipment. The data model built on the OPCUA foundation is three structures. The highest level consists of asset information, parameter, status, action, and the product. Asset information object consists of machine information and the machine specification, which contains basic information about the equipment and the key technical specification, like position, temperature, and so on. Parameter object contain information about the machine's user settings. The recipe part contains information on the set value for each product type. It is very important information because the setting values for producing good products are stored in the equipment. When the edge controller changes the injection molding condition, it changes the data here. We plan to add the machine setting that user cannot access under the name machine set part in the future. Sorry. Status objects show information about the state of the injection molding machine. Real-time part displays the sensor value or internal variable status that are updated periodically. When the OPCUA client requests, it sends the updated data at that time. The shot data part provides representative value for temperature, pressure, and so on that affect the quality of each process. This part is for communication with the MES system and is still used by most companies. In this project, we added 8 trace channels within shot data part. Each channel provides 10,000 samples of the time series data, and the sampling period can be adjusted from 1 millisecond to more. This provides the equivalent level of measurement data without using hard real-time Ethernet communication, so that it can be used in machine learning techniques. This graph above shows the data collected through the trace channel in Excel. These features are expected to continue to be utilized in the future. Action object provide an interact function between the injection molding machines and the auxiliary equipment. Although interlocking via hardware is common, it will be used to respond to remote control need of equipment through communication. Product object provide information about the products and currently in production. It gives you information about the name of the mold, how many you product produce at a time, what's your target production quantity, and so on. The contents of the data model introduced here will continue to be modified and added. Next, I'd like to show you a real picture of the test bed built at our company. It is configured the same as the actual injection molding environment, such as vision inspection equipment, takeout robot, and the raw material dryer. This is a vision inspection equipment. This here, the wireless router in the middle provides access to the cloud while exchanging Ethernet communication with auxiliary equipment. In fact, the research institute that carry out this project do not visit us, but take data directly and use it for research. The mini PC. The mini PC is here. This mini PC you see here is the edge controller. Since this test bed can collect more data than before and use it for analysis, we will continue to use it for research and the development of intelligent algorithm. The advantage of the edge controller is that it minimizes the additional computational burden on the existing control device in relation to the intelligence of the equipment. So it is less reluctant to commercialize and apply it. In addition, the edge controller can be used for various purposes, such as remote access to the injection molding machine controller and the remote program update functions. It is a supplement to the existing system, not a replacement. Therefore, we plan to apply this edge controller to our injection molding machine and sell it within a few years. I will conclude after explaining the future direction in terms of the data collection, storage, and management. Even now, customer companies install data server in the factory and collect and store data directly from injection molding machines. Each injection molding machine company has a separate data server for management. This is because each company has a different communication protocol. Recently, most injection molding machines companies support the OPC-UA communication method, and our company is the same. In case of OPC-UA communication, the communication protocol is well organized, and there are many commercialized communication software modules. So if the injection molding machine company defines the data model well, the client can collect the necessary data very simply. Therefore, today we introduce the data model of the injection molding machine we built while working on the development project. In addition, we suggested and showed that it is advantageous to use an edge controller to build an intelligent injection molding system or machine control system in the future, as well as data collection. That's all for the presentation. Thank you.
Thank you for your presentation. Yeah, today's presentation is done. Yeah, now we're gonna have a panel discussion, and it will be moderated by Mr. Sang-gun Yu, who is a Korean member of in S5. We will clear for a while. Wait a minute. Okay. Mr. Yu and other panel, so please come up to the stage.
Thank you. Please take a seat. Thank you. First of all, thank you for your patience for a very long time. So my name is Sang-gun Yu. I'm working for H3 Korea. And I've joined the panel discussion as a panel, but this is my first time to host the panel discussion, so I'm very pleased to be here. And I'm not sure this is the best choice to sit here and take a technical discussion rather than having fun in this beautiful island. But fortunately, it's getting dark and cold, so sitting here is better than going outside. So we have 2 questions for the panel. So as I let you know, we have question from Cass, and the second one is my own private questions. So as you know, we are living in the flood of technology such as digital twin, IoT, cloud, AR, VR, and even metaverse. So the first question is that what kind of standards will be, what can be applied to the factories in the coming decade? This is first question to you. So who will give the first answer?
So the question is what standards will be in place, yes, in 10 years from now?
To the factory.
Yes, to the factory, exactly. So I think there are different categories of standards that will be used. Of course, there are some standards that are developed and already put in place, and I think some of those will still be used. Mm-hmm. Today we heard about, for example, about IEC 61131 to program PLCs. That one has been around for a while. I think it actually will be there also in 10 years' time. Mm-hmm. Maybe some adjustments. Then there are standards that are now currently under development that maybe few companies today have tried, but I think more of those, they will be ready developed and also put in place. If I take an example, we spoke today about digital twin. I think this is something that standard that will be used much more in the future, to give one example. And then I think also there might be some standards that we haven't even started the development on yet. Mm-hmm. some things that are more, as I said before, circular manufacturing, what is needed in order to work even more with the sustainability issues. Even if those aspects are included in some of the standards, I think there will be specific standards that will also be put in place, and those will be also be used within 10 years. And yeah, most of those are under the umbrella of label of smart manufacturing.
That's right, yeah.
Yes, so these are some thoughts.
Yeah.
Thoughts, yes?
Yeah. You don't have any exact answer, so yeah, we can give freely our personal opinion in this time.
Okay, first of all, I agree to you, Charlotta, because I'm more than 20 years in the standardization, and existing standards will not go away. A lot of existing standards will also used in 20 years. Of course, you have always the tasks that some standards should be adapted for new technologies. I see what is coming up, that simulation works better together with real data. As you have seen here for the OpenX domain, where the streets and the scenarios artificial developed. At the end, you have also real cars, test cars, which drive outside, and these cars must fit at the end to the simulation data, and this should be mixed. And there's also other big task. This is the data evaluation, of course, because you must find out which is exactly the point. We have seen it today in the other presentation also, where is the critical situation, how should we act in the critical situation, and is this critical situation really reflected in the artificial situation? I think this is one of the most important things which will come up in the next time. Maybe not in 10 years, maybe in 5 years, to be honestly, but this is some of these requirements if automated driving shall be real valid.
Thank you. It is a tough question to me. But I think the standards goes together with the technology. So after 10 years, what technology will coming? Nobody knows. Because the NIST is the standards and technology. Standard and Technology, National Institute of Standard Technology. And CATS, Korea version, Korea Agency for Technology and Standard. So standard and technology is coming together. Technology after 10 years, we don't know yet. So I look back the 10 years ago, what was the technology at that time? And then I found that several of them, Kodak bankrupt. Nokia is still producing a smartphone, iPhone 5, and Galaxy 3. And then there's a patent war, Korea knows about that, between Apple and Samsung for 10 years, but they settled down at 10 years ago. After 10 years of a war, and NASA Curiosity touched Mars 10 years ago. And then finally, the Popular Science chose the innovation of the year was the Google Siri. Siri was the secretary, AI secretary. So maybe looking back 10 years, then we may expect what will happen after 10 years. That is my answer.
Professor Han mentioned about the standard and the technology. That's very interesting to me, about 10 years ago and maybe 10 years later. My view, I don't know other case like Google or smartphone or others, but I don't know. But in the manufacturing area, I have been more than 40 years history. So also I have been involved in a software area. So I think Charlotte Johnson mentioned about digital twin. I agree with her about her mention because of this twin is most important standard going to simulation. He mentioned about that, so I agree. Some of people mention about the metaverse manufacturing, metaverse for manufacturing. But my personal view, that's not too early stage in 10 years. So probably digital twin is more potential area for mega standardization. That's my view.
Yeah.
I'm not sure.
It's okay. Thank you for your answers. And 10 years ago, I had the joy in the development of sense network standards and IoT. After that, I am joining the digital twin project now. So 10 years ago, I could not imagine the kind of digital twin. Yeah, so that's funny. So I don't know what technology we have after 10 years now. So you're right. Anyway, my second question to you, as I mentioned before, is my private question, because this is what I am frequently asked in other events as a standard developer. So question is that, what do you think the field wants from the standards?
I start first. Because
Okay, because you are in the field.
That's an equal opportunity, okay? My personal view of which area wants from standardization. I think IIoT is IIoT with hard real-time application area is a very good area. We in Korea we can make a business to global. Ujin, he mentioned about injection, a smart injection machine system. That's very interesting because of most of people doesn't want to what is AI or what is digital twin, or it doesn't matter. They just manufacturing area. They just want to what is how much invest money, then what is we get. That's ROI. So I think smart like a dummy machine, like a not intelligent machine, make smarter. That is a very good area. We have to, Miss Korea, we have to focus on that. That's my personal idea. So I think legacy. My presentation, I already mentioned about the legacy machine. Still, 70% of total not integration in cyber area. So I think that's my personal opinion. So I always talking about how to integration of a legacy machine. That's what German people mention. SAP like greenfield and brownfield. They mentioned that. So that's one of. Also, Amazon mentioned about the green something else. So anyway, OPC UA or AAS is very important in future integration system. But we have to think about how to legacy data integration for manufacturing. Okay, that's my personal opinion. Yeah. That's it. Who is the next?
Second question is also tough to me because I'm from academy world, but the question is about industry. But as I heard from industry people, I want to talk about digital twin again. For me, metaverse and cyber physical system, augmented reality, digital twin are very similar. So that I see that there are big need from the industry. That's why there are so many different similar names there and developing. But my expectation is that among the similar technologies, digital twin is easy to remember. That's why I expect that digital twin will be more popular in industry. Thank you.
Yes, so I see the following things, and I think it have not changed in the last 20 years, and it will be also in the future, because at the end the standards are successfully which can be help to reach an easy exchangeability, and this requires, you have listened today in Charlotta's presentation, that a lot of companies have only a life duration from 15 years and go away. You should not look always to the big companies like Siemens and so on. There are a lot of small suppliers in the background, startups, which deliver something, and they need an easy level to implement the standard. So it should be easy understandable, first of all, the standard. It should be easy implementable, and it must have an acceptable cost level. If the border is too high to implement the standard will be at the end not successfully, and this can be supported by free available tooling, free available environments, which is outside the competition area of the product itself. And the second thing, which is for the standards important, now, that's the main difference to compare 20 years ago. 20 years ago, we were simple in the field bus area and have a little bit communication how this runs. Now, it have to integrate it in MES systems and so on, and this should fit together. So it does not help if you implement one standard but cannot solve the problem whole at the end. So the standard must fit together with the other standards, and that's what the field expects.
Yes, so some of my thoughts have been mentioned. One thing that I was thinking very much of when I had this question was this fact that the development is going faster and faster, and standards and technology, they are linked together. And that means that it also has to be possible to implement things much faster, like was mentioned here. So I think one thing that is requested or desired from industry is compatibility between the standards and maybe some guidelines on how they can be used together. Also in that piece of puzzle, it's also the fact that all the systems, they are modularized, but they become bigger and they are linked together in much bigger networks than they were before. So again, this interoperability between different standards, I think, will be very important.
Yeah.
Yes.
But this is important because you are leading the SE5, which cover the interoperability between the automation systems.
Yeah.
Okay, yeah. So thank you for your insight, and I will remember your answers when I ask same questions, and I use that. So this time I'd like to turn the microphone to the floor. So if you have any additional questions, please give your question to the panels. So anyone have questions to the panel? Silence means perfection. So,
do you want to finish the already?
yeah. Yeah. Okay. So thank you for your patience. Very late time, and thank you for all panels for your good answers to tough questions. So, and have a very good dinner and rest. Have a good night. Thank you.
Thank you.
안 가시죠? 예. Thank you for attending and see you later. Thank you. Okay. 참석자분들은 나가시면서 그 프론트 데스크에 저희가 조그만한 기념품을 준비했습니다. 예, 나가시면서 받아가시고 다시 한번 참석해 주셔서 감사합니다. 고맙습니다.